everyone, welcome to GemSeed class. As we all know, Touchdesigner has updated the latest purple pop operator group. Many students asked me what this operator group is used for. In fact, it has a lot of principles similar to SOP, but SOP runs on the CPU. So it can do a lot of things that we couldn't do before, and it can also run at a very fast speed. And like there are many operators in it, its functions are also difficult for us to create through other operators before. For example, the trailing effect of particles we saw this time may not be easy to do before, right? So now it can be realized through pop. And the whole implementation principle of the pop operator is different from the top, chop, and SOP we learned before. It will be more based on this attribute, that is the attributes of each of our model particles, to achieve various effects. I will give you an explanation later. Then we can get a general idea of the general principle of using pop to create in this lesson. Okay, so let's turn this off. So this latest version, it is an experimental version, not an official version, but an open beta version. How do we download it? And then we click the Get It Now button here in the upper right corner. So let's slide down to the bottom, and there's an experiment here. See? We click this download here, and we can see the 2025 version of the pop operator. Then we can download it here, both for your PC and Mac. As for Mac, it depends on whether your computer is Intel's chip or Apple's chip. Then we can click the next step after downloading. If you have a Touchdesigner on your computer, don't worry, it can install 2 Touchdesigners in parallel. 2, 3, or even 4. So in the process of your installation, remember that we need to click a small installation button of parallel install, and you can install 2 at the same time. Okay, let's open the latest version of the software. We're going to delete all of these, and then we're going to drag our model in. What I use here is a flower model. After we drag it in, it is automatically loaded in the form of a pop. So here we can do it in a new way, okay? When we clicked in, we found that it had an exclamation point. What did it say? It said that our current model does not have the 4 information of RGBA. So why? Actually, it has color. We know that RGBA stands for color, right? But we don't name it that way in this model. We can see color fields here, and we click on the small arrow on the right. Click, let's see how it is named. It is named after the full name of red, green, and blue, so we delete it. And it has no color, right? Then we select the corresponding red, green, blue here. Although it still has no color, we will solve it later, but at least it is correct. And there is no exclamation mark. I actually talked about it before in the previous tutorial. Why does our model have a pure white color after being imported? Let's first use our previous top form to give you a general explanation. Okay, let's see. And then what happens when we import a top format point cloud file? we will use a point file select to extract the color information in the file, right? Let's go back to the right here and select red, green and blue, and if we look at it in the normal color mode, it's also white, right? Why is that? In fact, as mentioned before, it is because the naming format of our data is different, right? Here we know that if we normally define a color, it is a color from 0 to 255, a range of values like 0 to 255, right? But in TD, we actually need to make it a range that varies from 0 to 1. So now we can click on the right here to see the value. It's too large, right? Red, green, and blue are all particularly large here, ranging from 0 to 255. But in fact, we need it to be in the range of 0 to 1. So let's wait a minute. This thing is actually called normalize. We can tell you about it later. We will talk about it later, so what we did before is we followed a math. And then we divided it by 255 in multi-add, and its color is correct, right? Because we are dividing 255 by 1, which is equivalent to turning it into a range from 0 to 1. Of course, we can also use a very good plugin on the YouTube I mentioned before, which can also restore our colors more accurately. Okay, so what do we do here? We can see that it is actually in the way of pop operators, and there is no way to select it for us alone. For example, the color information in this file, right? If we look at it, we will find that there are 3 small words in the lower left corner of our pop operator, which are P, N, and color. That represents the 3 pieces of information contained in our file, which are P for position. Then the second represents normal, and the third represents color, which is the position, normal, and color. Which is the orientation of each of our particles and color information, which is the 3 corresponding information here on the right. By the way, I forgot to remind you that if we import the model, remember not to have any Chinese or Chinese punctuation marks in this path. Even if you put it on the desktop, sometimes there may be Chinese because of the naming of your system, so try to put it under a certain disk. Let me reiterate here. Okay, to continue what we just said, this entire operator already contains P, N, and C, the 3 information, right? So we need to directly adjust the 3 information here. Here we will call this kind of information attribute, which we will often mention later. That is to say, we use a simpler way to understand it here. This is an attribute that each particle in our model represents. For example, P represents a property of a particle at which position in space it is located. So N represents this particle. It is no longer in 3-dimensional space. It is a directional property of the particle itself. What is color? Color means that each particle has its own color attribute, right? We will crazily add many interesting attributes here and make our final effect very rich. Then we just mentioned that our color is not right now. We see that it is called rearrange here, right? Change its range again. It's a bit like what we saw in math just now. There is also a range in math, right? We can also adjust our data range. So it's the same here. We're in rearrange and click on it. Then we click on scope, which means who are we going to control? We need to control the color. Well, we are in the map to high. That is, we adjust it with the highest value, divide by 255. Now we see that its color is correct, right? We adjusted the value of its color. Okay, so let's move on. We see on the right here is a little square that we don't want, right? We can delete it first. How to do it? There is an operator called delete in Pop we can use here. We can delete some of its points. What about deletion? It can create a box or circle for us, and we can delete anything outside or inside the box. Let's choose what attribute we want to adjust. We choose P, which means we need to deal with a change in its position, make an adjustment to its position. So now let's shrink the box. Our box is too big, right? We just deleted the entire model, so we reduced it and we can see the square grid, right? This is used to control the deletion of our point cloud. But what we want is to delete the outside, not the inside, right? Let's click invert. Can keep the things in box and then we zoom in. About this position, we can see it. Our flowers have been preserved and the outer squares have disappeared. And then we move on next to put our model in right place. We can use a transform. And then at align, here we call it align translate. Chong, these three XYZ are to origin. And it will automatically place our model at the world origin in this case. Our camera will be created later and we can shoot it directly. Okay, then let's move on. Let's render it now. We add a null after transform. Then we create another box. Use box as a single particle for our rendering, right? We're going to shrink this particle by 0.01 as a very small particle. Then we create a geo in the back to render the particle. Then go to our very common rendering 3-piece camera, light, and then render. We see the small particle in the center of the picture, right? Then we create a null in the back, show it on our background. And then we go to Geo, we can open instance, and then we drag null one to the top here. Why don't we drag this directly to translate? Because as we said just now, our model already contains all the attributes we need, right? We have the location, the orientation, and the color, so we just drag it to the top here. And then we're here at X, choose P0, P1, P2. And then the direction of it, we come to rotate to. Then we found rotate to in instance 2. Then we correspond to N0, N1, and N2. Then there is color, which corresponds to the color 0, color 2, and color 3. Then we go to transform and we turn it up a little bit. We can turn it up by 10, right? In this way, our model will be rendered, right? Okay, there's actually another way besides this one. Turn it off first. Actually, now we can create a geometry directly behind it through Pop. This can also be used for rendering, right? But personally, it may be slightly less controllable for me. I am still more accustomed to using instances so that students can make adjustments according to their own situation. For example, how can we adjust the attributes in this model to make some changes to our model? For example, our particle looks a bit boring now, right? It just put itself here. I want each particle to be able to rotate randomly. How can we do this? What do we control if we want particles to undergo a single rotation? N, right? N is the orientation of each of our particles. By controlling it, we can make our particles rotate. Okay, let's move these 3 forward. Let's make some adjustments in the middle. Let's create a noise in the middle. Noise was actually very common before, right? What happens to it automatically after we create it? It will give us the position, and the default is to give us the P attribute to add a change of noise, right? We've been talking about this all along, and it's a little boring, but what can we do here? Let's see, its output here means its output here. We just had it undergo a positional change, right? We changed our output by changing it to an N, which resulted in a change in the output for us. It's about changing one orientation of our normal model, right? So here we are, for example, we change it to 360. In this case, the range of all our changes is from 0 to 360 because we know that the orientation is a change from 0 to 360 degrees, right? Okay, now let's look at the difference. We can see that the orientation of this model has changed from a tight-fitting orientation to a 360-degree orientation with various variations, right? We can even lower its period so that there will be more detailed changes. So in this way, we have changed our normal. Of course, there are many ways to play, right? For example, we change P, which undergoes a 360-degree change based on the position of our model and then outputs it to the orientation for a change. But in this case, for example, we add a completely random change of orientation to it directly through noise. In this case, we can also see that it is basically a very chaotic state, right? But if we change it based on location here, it still looks a bit interesting. Then we go to transform and add an animation to it. In Translate 4D, we perform an expression for abs. Then we divide it by 10 to make it move, right? Does this expression, pay attention to capitalization, students? Okay, in that case, we will successfully make every particle of ours move. We can make our little particles a little bit smaller. Of course, it is good to adjust it according to personal preferences. Okay, then we go to add a black background. Add an RGB key and let's adjust the light. Then we open our shadow to make it have this shadow, right? Then, if our computer can handle it, we can increase the shadow resolution a little bit to make our projection more detailed. Then we can create a Phong material for it and drag it on. Okay, it's a little too dark now, right? We can also create an ambient light to illuminate our overall environment. We can slightly lower the ambient light and then, for example, increase it a little bit. Illuminate our shadows through ambient light. So just through a small case to tell you how we adjusted in Pop, right? If we use top, we may generate many nodes. Then, for example, using a single noise to scale it and then using a single noise to rotate in the instance. But here we can solve it all directly on this line, right? Okay, so now we're going to move on to something new, something more advanced, something interesting. All right, let's take it a little further at this time. We press the middle mouse button to create a particle. And we find that it comes directly with one, there's a particle, right? And when we open the particle, it has a lot more attributes than before, right? There are position, particle valve, particle ID, and many more, particle life expect, very many. Okay, so what we're going to do now is the emission of our particle and the trailing effect we're going to do later. Okay, we see the particles in their default state. When we input them, they generate particles based on the position of our model. Let's adjust its parameters here. For example, if I want this particle to move upwards, we can change it to 0.0.5 in the initial velocity, which means it is in an upward emission state, right? Then, for example, if we want our particles to emit more, we change the birth rate from 10 to 300. All of a sudden, our particles are going to emit more and shoot it up, right? Then we know that every particle has a life cycle, right? The possible existence time of each particle is fixed. We have a life expectation here. Let's make it smaller so that it doesn't float so far. Let these particles float for 3 seconds and disappear. Then, for example, we can add a life variance to it, which can make the growth time of each of our particles slightly different. Then we create a noise behind it, and we see that by adding a noise, our particles have changed from a state of flying up in a daze to a state of flying in a mess. Okay, and then we go on, we can adjust this parameter slightly, for example, by increasing the period and then increasing the harmonics. Then the amplitude can be slightly reduced without changing so much, right? What does our output show us? The output is a noise added to the position of each of our particles. So here we just need to have it add a slightly messy particle change to our x-axis and z-axis directions, so we add a.xz after p. This means that now we only need to adjust the changes on the x-axis and z-axis, without adding a change on the y-axis, which is the velocity at which our particles are emitted upwards. Of course, we can also add this change to the transform to make it more variable. We can simply copy the expression from earlier. Okay, then we move it up a little bit, create a null at the back, and drag the null onto the particle. Select the first target particle update pop, which is here. Let's put it here. And in this way, we can see what the difference is. We turn it off. At the beginning, our particles ran upwards in a straight and upright manner, right? But if we drag it up, it will launch in the direction of the last one we dragged in, which is null-free. In this way, it can bring more changes and diversity to our entire particle emission. Then we add a new operator called trail after null-3. This is a completely new operator that has never been seen before, right? We see that when we add it in, it has some problems, right? It connects all our particles together, which is actually a great aspect of our pop. If this thing is implemented in SOP, it may be very slow, right? But let's see that we are still running at a speed of 60 frames per second. But what we actually want is for the particles to have a trailing effect. Why does it connect all the particles here? This is definitely wrong. We need to make some adjustments in the particle. We need to change the point ID reuse in the particle. We see that our default option is reuse point IDs in loop, which means that each particle has its own unique ID, meaning it has its own name. That is to say, the name of our particle, when it disappears, will continue to be reused. So in this case, because our trial will connect based on the particle ID, right? If it keeps being reused like this, it will connect the front and back together like this. So we're going to adjust here. We changed it to don't reuse. Then we will open it here called match by attribute, which means we will perform a match with a certain attribute mentioned earlier. We'll use the part ID we just modified for the properties here, and we'll see if it's successful, right? It is to match all our generated small tails with our ID. Okay, so here we can make an adjustment. For example, the trail length, which is the length of our trail, we can change it to 3 and its trail will be longer. Of course, it doesn't matter if we adjust it according to our own preferences. Then we add a geo after it and render it. Actually, we can see our small trailing particles being emitted like this, right? We can adjust our camera so that we can see more clearly. A little bit back and then a little bit up. Okay. But now it may seem a little boring, right? Just some white lines keep going up and up, right? Then we can make more adjustments to it.